You've seen what types of sensors and outputs are used in late model vehicles, and you've also seen how these sensors and outputs are incorporated into automotive circuits and how those circuits operate. Now you'll see how to apply your knowledge of computer-controlled circuits to diagnose problems in the circuits. Your most important diagnostic tool is your brain, but you'll still need a digital multimeter, a scan tool, and oscilloscope to diagnose problems with computer-controlled circuits. The mill is often the only thing a customer will notice if the engine management system reports a malfunction. When the ECM or PCM detects an emission-related malfunction during the first driving cycle, the DTC and engine data are stored in the freeze frame memory. The mill is illuminated when the ECM or PCM detects the same malfunction related to the DTC in 2 consecutive driving cycles. Note, the mill may illuminate even though the vehicle seems to be running normally and there are no apparent drivability problems. The presence of the light indicates to the driver that an emissions-related concern has occurred. The light can either illuminate continuously, indicating a potential system malfunction, or flash, indicating potential catalytic converter damage is possible. Diagnostic trouble codes, or DTCs, are electronic signals stored in the ECM. They indicate the presence of a fault detected by the ECM. Many malfunctions with sensors and engine output circuits, particularly those involved with powertrain control and emissions, are likely to set a trouble code. Once you have a code, the service literature provides an easy-to-follow routine for getting to the root cause of the diagnostic code. Retrieving codes using the scan tool is performed by 1. Connecting the DLC cable to the OBD2 connector and turning on the Vehicle Communication Interface, or VCI, to communicate with the scan tool. 2. Selecting the vehicle through the options displayed on the various scan tool menus. 3. Performing fault code searching to identify vehicle code faults for all systems. 4. Clicking on a code for DTC status, active, or history screen. What happens when something in the system triggers a code? Along with the DTC, the ECM stores information that provides a snapshot of what was happening in the engine management system when the vehicle's check engine light came on. This information is called freeze frame data. Freeze frame data is a recording of the real-time sensor information at the time the DTC was triggered. Freeze frame data is very useful for diagnosis. Specific engine parameters that are recorded include engine load, engine RPM, fuel trim value, fuel pressure if available, vehicle speed if available, engine coolant temperature, airflow, intake manifold pressure if available, open or closed loop status, and fault code. Real-time parameter, or PID data, is also available using the scan tool. If you suspect a malfunction with a circuit that didn't set a code, you can monitor the circuit data in real time and look for anomalies, such as the unexpected voltage in spikes that indicate an intermittent condition. You can also try wiggling a harness to see if an intermittent short or open connection might be occurring. In the example shown here, the map sensor data is being monitored in a graph output. If you were diagnosing a drivability concern, you could verify that the circuit is functioning properly without having to check the circuit with a digital multimeter. Note that in many cases, PID data is calculated or presented on the scan tool in an interpreted format. For example, barometric pressure is converted to PSI for display on the scan tool. You can't always assume that a circuit is operating correctly even when the PID data seems to be within specification. Certain circuits will display a pre-programmed fail-safe value after the DTC has set. Typically, once a fault has been identified, the diagnostic routine in the service manual will instruct you to perform checks of the circuit. Whether or not you have a code, you should know how to diagnose a sensor circuit. Depending on the type of sensor, you might check voltage in the harness or resistance of the component. Let's start with resistance. Measuring resistance is the process of measuring the resistance to the flow of electrons through the circuit. Many sensors, such as an ECT sensor, provide resistance to current flow. Some components, such as a motor, have long lengths of wire in the form of a coil. A break in a wire or excessive corrosion can cause excessive resistance or an open circuit. To check the resistance of a sensor or component, turn the vehicle power off. Isolate the component or the portion of the circuit to be tested. Attach the test leads to the correct input terminals on the DMM to measure resistance. Set the mode switch to ohms. Connect one test lead to each end of the electrical component or section of the circuit to be tested. Note the reading on the display. Compare the reading to the specifications in the service manual. If terminals are difficult to access, you may need to use adapters or back probe the connectors to make resistance measurements. Be sure not to damage the connectors or wiring. A switch, such as the brake switch, functions as a sensor when wired to a control module. In the case of the brake switch, you should see 12 volts at the switch when the brake pedal is depressed and 0 volts when it is released. In some circuits, such as the MAF sensor circuit, supply voltage is provided to power the sensor. Always check the service manual to determine expected voltage on a given circuit. If the terminals are difficult to access, you may need to use adapters or back probe the connectors to make voltage measurements. Be sure not to damage the connectors or a voltage drop check is used to determine if any connector, wire, or component in the circuit has excessive resistance, which means it is consuming too much electricity. To measure voltage drop, place the DMM test leads across a fuse, switch, load, or other test point. This test is used to determine excessive resistance by measuring voltage drop across the component while current is flowing. In a circuit with only one load, the load should use up all the voltage. In a circuit with more than one load, the resistance of the load determines how much voltage it uses. Excessive resistance on the ground side of a circuit can cause excessive voltage drop also. Check the circuit for corrosion or loose or dirty connections. Many sensor circuits use reference voltage from the ECM, providing a 5-volt reference voltage to the sensor. For this ECT circuit, 2 wires are used, a ground and a reference voltage. Depending on temperature, the voltage on the signal side should vary between 0 and 5 volts. For a MAP sensor, a 3-wire circuit is used. You should expect 5 volts at the reference circuit and something between 0 and 5 volts at the signal circuit. With the ignition on, check the voltage at the sensor connector. The problem could be a shorted or open circuit, depending on the circuit and the type of sensor used. With this in mind, correct voltage to any component needs to be checked with the sensor unplugged and plugged in. This MAP circuit also uses reference voltage. If the reference wire voltage is within spec 5 volts and signal voltage is out of spec, check the voltage on the ground wire. The voltage on the signal wire should vary between approximately 0.5 and 4.5 volts as the throttle is opened and closed. At low manifold pressure, at idle for example, output voltage on the signal wire is low. At high manifold pressure, open throttle, voltage on the signal wire is high. Measuring current or amperage in a circuit requires that you connect the meter in series with the circuit. Most commercially available DMMs can measure current that does not exceed 10 amps. To measure current with a DMM on a generator, the circuit must be live, powered by a battery or running. Make a break in the circuit at a connector or another easy location in the circuit, then use the DMM leads in the series to complete the circuit. With the DMM connected in series to complete the circuit, apply power to the circuit and take a reading. The DMM becomes part of the circuit and current flows through the meter. You can think of the DMM as a jumper wire. When measuring DC current above 10 amps, use an inductive clamp. For example, you can measure the alternator output with an inductive clamp. A useful application of checking low current is the test for parasitic drain. When a car battery discharges overnight, it usually indicates the battery is nearing the end of its useful life, or that the driver or a passenger left something turned on. Occasionally, however, some circuits may draw excess current from the battery. This is called parasitic draw. Some parasitic draw is normal for circuits such as clocks, computer memory, and alarms. Over time, these can discharge a battery if the vehicle is not driven regularly. It becomes a problem when the draw exceeds the parasitic draw specification established for the vehicle. You can use a DMM to troubleshoot a parasitic draw problem. If current draw exceeds 35 to 40 milliamps, you'll need to diagnose the source of the excess current draw. Make sure all loads are off, all doors closed, and ignition switch is not on. Set up the DMM to measure milliamps. Install a jumper or use a battery disconnect to ensure that the current is supplied from the battery to the vehicle's circuits or through the meter when taking a current measurement. Don't remove the battery terminal, then insert the meter in series. During the delay of making the connection, the body control module may time out and a potential cause of the drain may be removed. Once the meter leads are installed, disconnect the battery from the circuit. The DMM displays the current. Remove fuses until the current drops to the level indicated. Refer to the schematic in the service literature to determine which circuits are powered through that fuse. Some sensor circuits cannot be easily diagnosed with a DMM. Digital signals, duty cycle, and pulse width modulated signals are all easier and more accurate to interpret using an oscilloscope rather than a digital multimeter. For example, you can compare oscilloscope patterns of CMP or CKP signals to known good waveforms as shown in the service literature. Additionally, you can also check the on time of a solenoid. For example, you can check fuel injector pulse width on the oscilloscope. You can also check MAF frequency on the oscilloscope. You can't check the MAF signal on a DMM. You must check the frequency on a scope for given airflow at various RPM ranges. Depending on the vehicle, sensors and switches may be wired directly to a module. However, it's quite common that information from a sensor is needed by more than one module. Rather than wiring the sensor directly to more than one module, a data bus is used to relay data from the sensor from one module to another. This reduces the amount of wiring used in a vehicle. In the example shown here, yaw sensor data is placed on the bus for use by several modules.